Today we're going to be looking at exponential models. And the first thing we're going to look at is something called exponential growth. So any quantity that increases according to an exponential function, and that is anything in the form of y equals b a to the power of x, where a is a number greater than 1, is showing what we call exponential growth. So something that grows exponentially increases slowly at first, but then becomes quicker and quicker. So for example, population size, an investment that gets compound interest, a flu or a computer virus starts out slowly, gets bigger and bigger, and a bushfire starts out small, gets bigger and bigger. All examples of exponential growth. So here I have a picture or an example where we're looking at an exponential function. So here I've been told that my exponential function is this graph of p equals 5001 plus 0.09 to the t. And it's modeling the population of an island where p is the population and t is the time in years. And we've drawn it here. And the first question says, which part of the exponential curve applies to this population model in this case? So this graph is showing you the entire graph, but I'm not interested in anything over on this side. And if you think about it, it's because this is showing time and I can't have negative time. So I'm only interested where t is greater than or equal to 0. That's the only part of the graph that I'm interested in. And then we just have a few questions to answer. What was the initial population on the island? Well, the initial population happens when time is 0. What is it? So if I look at my graph, at the start, there were 5,000 people on the island. And then it says use the graph to estimate the population after 12 years. So I'm going to be estimating this. So I'm just going to have a look at where is 12 years. So 12 years looks like it could possibly be around about here. So I'm going to draw my dotted line up and I'm going to come over and have a read off there. So that looks to me like it's around 14,000 people. And how long did it take for the population to double? So if I think about my initial population being 5,000, if I double that, that's 10,000. So once more, I'm going to go to my graph. And using my dotted lines, I'm going to look, and it looks like it's approximately 8 years. So approximately 8 years. So that's not too bad. Let's have a look at exponential decay. So in exponential decay, any quantity that is decreasing, and have a look at my function, the thing that shows me that it's decreasing is this negative x. Or we can have it looking like this, where a is between 0 and 1. These things show me exponential decay. So it's going to be the same graph, but it's just going to be going in the opposite direction. So anything that decays exponentially decreases quickly at first and then goes more slowly. So for example, radioactive decay, the cooling of hot liquid, and a declining balance depreciation. So we've already looked at this sort of graph. So let's look at it mathematically. In this example, we have a rubber ball being dropped from a balcony. So if you imagine that rubber ball, it's going to hit the ground, it's going to go up, down, up, down, up, down, up, down, up, down, up, down, blah, blah, blah. So this is an example of an exponential curve. So in this case, this is what we are told, where b is the number of bounces. And it says calculate to the nearest centimetre the height of the ball above the ground after the 5th bounce. So we'll be giving b equals 5. So we're going to use this formula, 12, and remember there's really a time sign here, 0.6 to the power of 5. So picking up your calculators, you get 0.93312 meters. Question says to the nearest centimetre, so it might be easier, since we're looking at this great big decimal, to change it into centimetres by multiplying by 100. And to the nearest centimetre, that's going to be approximately 93 centimetres. The next part says graph the function for values of b from 0 to 8. So I'm going to get you to fill in the table and plot the graph. So pause the video, have a go, and then come back and check your answers. So having a look, I just rounded to 1 decimal place and I graphed this as very best as I could. Now we can see it's an exponential curve, it's a negative one, and we've looked at positive and negative in the previous lesson. So now there were just a couple of questions to answer. So let's have a go at looking at those. So the first question says, what is the height from which the ball was first dropped? Well, when the first ball was first dropped, that means there were no bounces. So if I look at my graph, my height is 12. And this graph should actually say meters. So that is 12 meters. The next thing says, estimate after which bounce the ball will rise to 12 centimeters. So 12 centimeters is the height. So that is 0.12 meters. So now we're going to be estimating. We could try and read it off my graph. It seems very, very difficult. Or we could just try and do a guess and check from our actual formula. So the formula we have for h equals 12 and 0.6 to the power of b. So we want h to get as close to 0.12 as possible. So what I can do is I can try some numbers. So let's try, say, 10. So if I put this in, because I'm just guessing and checking, I get 0.07255. Well, that's not going to work. That's way too small. So let's try another guess. And I could try, say, 8. Now, if I used 8, I get 0.2155. Well, that's too big. So let's try 9. Substituting that and getting that into my calculator to get 0.1209. So estimate the height. The height is approximately 9. So this means that at the 9th bounce, the height would reach 12 centimeters. So the bounce is the 9th bounce. And then the last question says, what are the limitations of this exponential for very large values of b? Well, if you think about this, if you did do this experiment, you've seen in real life that the ball actually does stop bouncing. So the ball will not bounce forever. So for very large values of b, this exponential graph just stops working. So you need to write something like that. If you've got any questions, ask me in class.